So this video is going to focus on atomic mass calculations. So for this discussion, you probably want to get out a calculator and follow along with me and try the calculations on your own. So atomic mass, or what the Webb Elements periodic table calls it, atomic weight, just depends upon the author of the periodic table. Atomic mass is what we call weighted average, okay? And if you are in Algebra 2 or even algebra, you would have been exposed to something called a weighted average. So everything in high school or at our high school is based off of 85% of your grade is based off of your coursework, 15% is your final. That is a weighted average. So not all of the points that you get are going to be equally weighted. So same thing goes for the periodic table. So the periodic table is based off the standard, carbon 12, okay? So carbon 12 is essentially the isotope of carbon that is about 99% of the carbon that we have. So that means carbon has 6 protons and 6 neutrons is that particular isotope. There are other isotopes. So since this is the standard, they have established that a proton in this particular isotope is equal to what we call a 1 AMU. Okay, and AMU stands for atomic mass units. You don't really need to know what that is, but that is a unit that you're going to see in something called mass spectrometry that we're going to do later this year. And so it's going to be a number that you're going to see. So it also applies to any neutron that is in this particular isotope is also 1 AMU. So what we're going to look at is how is this particular atomic mass calculated? How is it calculated? So when we are discussing isotopes, since isotopes have different number of protons and neutrons, we need to do what we call a weighted average, okay? So we are going to look at this example. Chlorine happens to have 2 naturally occurring isotopes, okay? So 2 isotopes. So it is chlorine 35, that is its mass number, and chlorine 37. About 75% of chlorine 35 is the chlorine that we have on this planet, 25% is chlorine 37. Well, we have masses of each one of these because these are all according to carbon 12. So that is why you don't see 35 AMUs here and 37 AMUs, because this is not carbon 12. So everything is based off of that standard. So what we're going to do is we're going to take these numbers and we're going to do what we call a weighted average. Now, if this happened to be 50-50, all we would have to do is take these 2 masses, add them together and divide by 2, like you do an average mass. But because this is 75% this and 25% of this, we can't take them as equal value. The other thing I want you to consider is our mass, our overall mass of all of the chlorine has to be somewhere between 35 and 37, between these 2 masses. And you should understand that if 75% of it is chlorine 35, most of your mass should be closer to this number than it is to this number. So we're going to do a weighted average, okay? So we are going to take 75% and multiply it by the mass, 25% multiply by this mass. But we're not going to do that. We're going to do it in decimals. So we're going to move the decimal point 2 over. We're going to multiply it by the decimal. Okay. So we're going to take 0.75 times 34.969 AMUs, and we're going to add it to 0.25, 36.96 AMUs, and we're going to add those together. That's how you do a weighted average. So again, going back to your grade, 85% times what your percentage is times 15%. A lot of you have tried to figure out what you needed on the final to get that. When you do the math here, it comes out to be about 35.468 AMUs. And depending upon your periodic table, if you look up chlorine on a periodic table, you will see the number underneath, which is 35.45. This one is 35.468. It depends upon the numbers that I pulled from. So this is what we call your weighted average of all of the chlorine that exists. And so it's going to include all of the different isotopes that you see. So this is a pretty simple, straightforward calculation. So I am going to have a little bit of a twist on this calculation because we are looking at a kind of expanding your math skills here in this course. So I'm going to have you look at the next example. We have boron 10 and boron 11. And these types of calculations can only be done with two isotopes. So I have a mass here, okay, in AMUs. I don't know the percentages, but I know the overall, meaning if I look up boron on the periodic table, I will see that its atomic mass is 10.81, okay? And again, it's due to the fact that you have two of these isotopes. So 10.81, I'm probably having more of the boron 11 than I do the boron 10 just by looking at the numbers here. Okay, so how do I do something like this? Well, I have to set this one to X, and I can't set this one to Y, because if I set this one to Y, I don't have two equations here that I could do two equations with. So instead, I have to change this to another variable. Well, going back to our previous example, okay, if I look at my decimals here of 0.75 and 0.25, if I add these up, what do I get? I get the number 1, okay? So if one isotope is 0.75, the other one has to be 1 minus that is 0.25. So knowing that, I could set this as 1 minus x. I could set that as 1 minus x. So setting this up, I'm going to just shift it over to another piece of paper here, where I've done all of the calculations ahead of time. Okay, so what I have to do, if this is x and this is 1 minus x, I then have to plug in these x values where I would put the decimal. Okay, so going back to that previous example. So I have to take x times the mass plus my variable here is 1 minus x. And please be careful, you can't do x minus 1. That will not work mathematically. Times the mass is equal to the overall mass, okay, the mass we get on the periodic table. So if I take this and I just do some simple algebra, okay, so I take the algebra skills that I have and I take a look at those, okay. So I am going to multiply through. So I have 10.012x plus I take 1 times that number minus x times that number is equal to this number. So I've done nothing to the right-hand side. So then I gather everything that has an x to it. And don't worry that they come out to be a negative value. So when I put these two together, I get a negative 0.997x. And then if I bring the 11 over here, so realize I'm bringing the number 11.009 and subtracting it from 10.810, I get a negative 0.199, okay? So when I divide both of these sides by, again, negative 0.997 to get the x by itself, I get the x being 0.199 and 1 minus x as being 0.801. So this comes out to be 19% of it is boron 10, which I predicted that would be the smaller one, and 80.1% for the other isotope. All right, so the last one I've given you here is kind of your practice for the same calculation, And I would suggest that you try to pause the video, see if you could do it, and then I will show the answers. So take a moment, see if you could try this calculation on your own, and then I will show you the answer. So here we have essentially the solution to this problem. So again, you go through the same algebra as before, I've just changed the numbers. And so you should end up with AG 107 being about 51.8%. And then the other one, the AG 109 at being 48.2%. So again, go through the math, double check that you put everything the same in your calculator, and that's going to be how you do those calculations.